Welcome, everyone, to tonight's journey into the microscopic world where chemistry shapes our lives in profound ways. Tonight, we delve into the realm of organic synthetic chemistry, specifically focusing on the unsung heroes of molecule making, catalysts. These remarkable substances, often used in minuscule amounts, possess the extraordinary ability to accelerate chemical reactions, enabling the efficient construction of complex molecules, including many of the modern medicines we rely on. Prepare to be amazed as we uncover the secrets of how catalysts work, their diverse applications, and the fascinating stories behind their discovery. Imagine a bustling construction site where workers are struggling to assemble a complex structure. Now, picture a skilled foreman arriving on the scene, providing guidance and tools that dramatically speed up the construction process. Catalysts play a similar role in chemical reactions. They provide an alternative reaction pathway with a lower activation energy, meaning that less energy is required for the reaction to occur. This allows reactions to proceed much faster, often millions of times faster than they would without the catalyst. This acceleration is crucial in the synthesis of pharmaceuticals, where time and efficiency are of the essence. One of the most remarkable aspects of catalysts is their ability to remain unchanged at the end of a reaction. They participate in the reaction mechanism, but they are not consumed in the process. This means that a single catalyst molecule can facilitate the formation of countless product molecules, making them incredibly efficient and cost-effective. Think of a catalyst as a master key that can unlock many doors without being worn down. This turnover number, as it's called, is a critical metric for evaluating the effectiveness of catalyst. A high turnover number indicates that the catalyst is highly active and can facilitate a large number of reactions before it becomes deactivated or loses its effectiveness. Catalysts come in a wide variety of forms, each with its own unique properties and applications. Some catalysts are simple inorganic compounds, such as metal oxides or acids, while others are complex organic molecules, such as enzymes or organometallic complexes. The choice of catalyst depends on the specific reaction being carried out and the desired outcome. For example, metal catalysts, such as palladium and platinum, are widely used in carbon-carbon bond-forming reactions, which are essential for building the carbon skeletons of many organic molecules. Enzyme catalysts, on the other hand, are highly specific and can catalyze reactions with remarkable precision, often mimicking the intricate processes that occur in living cells. Consider the synthesis of ibuprofen, a common pain reliever. The original synthesis of ibuprofen involved a multi-step process with low overall yield and significant waste generation. However, with the development of a catalytic process, the synthesis became much more efficient, with fewer steps, higher yield, and reduced waste. This catalytic process not only made ibuprofen more affordable, but also significantly reduced its environmental impact. This example highlights the power of catalysis to transform chemical manufacturing, making it more sustainable and economically viable. Now, let's delve into the fascinating world of enzyme catalysis. Enzymes are nature's catalysts, highly specialized proteins that catalyze biochemical reactions with incredible speed and precision. They are essential for life, enabling the myriad of chemical reactions that occur within our cells. Enzymes work by binding to specific molecules, called substrates, and facilitating their conversion into products. The active site of an enzyme, a small pocket within the protein structure, is perfectly shaped to bind the substrate and catalyze the reaction. This locking key mechanism ensures that the enzyme only catalyzes the intended reaction, preventing unwanted side reactions. One of the most remarkable examples of enzyme catalysis is the nitrogenase enzyme, which catalyzes the conversion of atmospheric nitrogen into ammonia, a crucial nutrient for plants. This reaction is extremely difficult to carry out chemically, requiring high temperatures and pressures. However, the nitrogenase enzyme performs this reaction at ambient temperature and pressure with remarkable efficiency. This enzyme is essential for the nitrogen cycle, which is vital for maintaining the fertility of our soils and supporting plant growth. Scientists are actively studying the nitrogenase enzyme to develop new catalysts that can mimic its activity, potentially leading to more sustainable methods for producing ammonia fertilizer. Another area where catalysts are making a significant impact is in the development of green chemistry. Green chemistry aims to design chemical processes that are environmentally friendly, minimizing waste, reducing energy consumption, and using renewable resources. Catalysts play a central role in green chemistry by enabling more efficient and selective reactions, reducing the need for harsh reagents and solvents. For example, catalysts can be used to convert waste biomass into valuable chemicals and fuels, reducing our reliance on fossil fuels and mitigating climate change. The development of new and improved catalysts is crucial for achieving the goals of green chemistry and creating a more sustainable future. Asymmetric catalysis is a particularly fascinating area of catalysis that focuses on the synthesis of chiral molecules. Chiral molecules are molecules that are non-superimposable mirror images of each other, like our left and right hands. Many pharmaceuticals are chiral, and the two mirror images, or enantiomers, can have different biological activities. In some cases, one enantiomer may be therapeutic while the other is toxic. Asymmetric catalysis allows chemists to selectively synthesize one enantiomer over the other, ensuring that the desired therapeutic effect is achieved without unwanted side effects. This is particularly important in the development of new drugs, where the purity and safety of the final product are paramount. Consider the development of a new drug for treating Parkinson's disease. The drug is a chiral molecule, and only one of the enantiomers is effective in treating the disease. The other enantiomer is not only ineffective, but also causes unwanted side effects. Using asymmetric catalysis, chemists can selectively synthesize the desired enantiomer in high purity, ensuring that the drug is safe and effective for patients. This example highlights the importance of asymmetric catalysis in the development of new and improved pharmaceuticals. The history of catalysis is filled with remarkable discoveries and innovations. One of the earliest examples of catalysis dates back to the early 19th century when Humphrey Davy observed that platinum could catalyze the oxidation of hydrogen. This discovery paved the way for the development of many other catalytic processes, including the Haber-Bosch process for the synthesis of ammonia, which revolutionized agriculture and helped feed the world. The Haber-Bosch process, developed in the early 20th century by Fritz Haber and Carl Bosch, uses an iron catalyst to convert atmospheric nitrogen and hydrogen into ammonia. This process is estimated to be responsible for sustaining about half of the world's population, highlighting the profound impact of catalysis on human society. In the mid-20th century, Carl Ziegler and Giulio Natta made groundbreaking discoveries in the field of polymerization catalysis, leading to the development of new polymers with improved properties. Ziegler and Natta discovered that certain metal catalysts could polymerize alkenes, such as ethylene and propylene, into long chains of repeating units, forming polymers like polyethylene and polypropylene. These polymers have a wide range of applications, from plastic bags and containers to textiles and automotive parts. The work of Ziegler and Natta revolutionized the plastics industry and earned them the Nobel Prize in Chemistry in 1963. Today, catalysis continues to be a vibrant and rapidly evolving field of research. Scientists are constantly developing new and improved catalysts with enhanced activity, selectivity, and stability. They are also exploring new applications of catalysis in areas such as energy, material science, and environmental remediation. The development of new catalysts is essential for addressing some of the most pressing challenges facing our society, including climate change, resource scarcity, and disease. One of the most exciting areas of research in catalysis is the development of single-atom catalysts. Single-atom catalysts consist of individual metal atoms dispersed on a support material, such as a metal oxide or a carbon material. These catalysts exhibit unique catalytic properties due to their high surface area and the electronic properties of the isolated metal atoms. Single-atom catalysts have shown promising results in a variety of reactions, including oxidation, reduction, and carbon-carbon bond formation. The development of single-atom catalysts is still in its early stages, but they hold great potential for revolutionizing catalysis and enabling new chemical transformations. Another emerging area of research is the use of computational methods to design and optimize catalysts. Computational chemistry allows scientists to simulate chemical reactions and predict the properties of catalysts before they are synthesized in a laboratory. This can significantly speed up the discovery process and reduce the cost of developing new catalysts. Computational methods are also being used to understand the mechanisms of catalytic reactions, providing valuable insights into how catalysts work and how they can be improved. The combination of experimental and computational approaches is driving rapid progress in the field of catalysis. As we conclude tonight's exploration of catalysts, let us reflect on the profound impact these tiny molecules have on our world. From the medicines that heal us to the materials that build our homes, catalysts are essential for countless chemical processes that shape our lives. Their ability to accelerate reactions, reduce waste, and enable the synthesis of complex molecules makes them indispensable tools for chemists and engineers. As we continue to develop new and improved catalysts, we can look forward to a future where chemistry plays an even greater role in solving some of the most pressing challenges facing our society. The journey into the world of catalysts is a journey into the heart of chemistry, a world of endless possibilities and remarkable discoveries. The beauty of catalysis lies not only in its practical applications, but also in its fundamental scientific principles. Understanding how catalysts work requires a deep understanding of chemical kinetics, thermodynamics, and quantum mechanics. Catalysis is a multidisciplinary field that brings together chemists, physicists, and engineers to solve complex problems and create new technologies. The study of catalysis is not just about making new molecules. It's about understanding the fundamental laws of nature and using them to our advantage. It's about harnessing the power of chemistry to create a better world. Consider the intricate dance of electrons and atoms that occurs on the surface of a catalyst during a chemical reaction. Electrons flow from one molecule to another. Bonds are broken and formed, and the catalyst facilitates this transformation with remarkable precision. The catalyst acts as a mediator, bringing the reactants together in the right orientation and lowering the energy barrier for the reaction to occur. This dance of electrons and atoms is governed by the laws of quantum mechanics, which describe the behavior of matter at the atomic and subatomic level. Understanding these quantum mechanical principles is essential for designing new and improved catalysts. The development of new catalysts is not just a matter of trial and error. It's a process that requires careful planning, experimentation, and analysis. Chemists use a variety of techniques to characterize catalysts, including spectroscopy, microscopy, and diffraction. These techniques provide information about the structure, composition, and electronic properties of catalysts, allowing chemists to understand how they work and how they can be improved. The development of new catalysts is a challenging but rewarding endeavor that can have a profound impact on our world. As we drift further into the realm of sleep, let us carry with us the image of these tireless molecular machines, silently and efficiently transforming the world around us. Catalysts are a testament to the power of human ingenuity and the beauty of chemistry. They're a reminder that even the smallest things can have a profound impact on our lives. So, close your eyes and imagine the intricate dance of atoms and electrons, the silent symphony of chemical reactions, and the endless possibilities of catalysis. May your dreams be filled with the wonders of science and the promise of a brighter future. And as you begin to fall asleep, think about the countless reactions happening within your own body, many of which are catalyzed by enzymes. These biological catalysts are essential for life, enabling the complex biochemical processes that keep us alive and functioning. From the digestion of food to the synthesis of DNA, enzymes play a crucial role in nearly every biological process. They are incredibly efficient and specific, able to accelerate reactions by factors of millions or even billions. Understanding how enzymes work has been a major focus of research in biochemistry and has led to the development of many important drugs and therapies. Imagine the intricate machinery of an enzyme, precisely positioning molecules and facilitating the flow of electrons to create new products. It's a microscopic world of incredible complexity and beauty, all powered by the principles of catalysis. Enzymes, these remarkable biological catalysts, are not just simple molecules. They're intricate protein structures, carefully folded into three-dimensional shapes that dictate their function. Think of them as tiny, highly specialized machines, each designed to catalyze a specific reaction with incredible precision. The active site of an enzyme, the region where the reaction takes place, is a carefully crafted pocket that binds to the reactant molecule or substrate and lowers the activation energy required for the reaction to occur. This intricate interaction between enzyme and substrate is often described using the lock and key model, where the enzyme and substrate fit together perfectly, like a key fitting into a lock. However, a more accurate model, the induced fit model, suggests that the enzyme can change its shape slightly to better accommodate the substrate, further optimizing the reaction. The specificity of enzymes is what allows them to catalyze only certain reactions, preventing unwanted side reactions and ensuring that biological processes occur with remarkable efficiency. Without enzymes, the reactions necessary for life would be too slow to sustain life as we know it. The study of enzymes has revolutionized our understanding of biology and medicine. By understanding how enzymes work, we can develop drugs that target specific enzymes involved in disease processes. For example, many drugs used to treat HIV work by inhibiting the enzyme reverse transcriptase, which is essential for the virus to replicate. Similarly, statins, drugs used to lower cholesterol, work by inhibiting an enzyme involved in cholesterol synthesis. The ability to design drugs that selectively target enzymes has led to the development of more effective and less toxic therapies. Imagine the possibilities for future drug development as we continue to learn more about the intricate workings of enzymes. We may one day be able to design drugs that can cure diseases that are currently untreatable. The journey into the world of enzymes is a journey into the heart of life itself. And as you continue to relax, consider the industrial applications of catalysis. Catalysts are used in the production of a vast array of products, from plastics and fuels to fertilizers and pharmaceuticals. The chemical industry relies heavily on catalysts to accelerate reactions, reduce waste, and lower production costs. For example, the Haber-Bosch process, which uses an iron catalyst to convert nitrogen and hydrogen into ammonia, is one of the most important industrial processes in the world. Ammonia is a key ingredient in fertilizers, which are essential for modern agriculture. Without the Haber-Bosch process, we would not be able to produce enough food to feed the world's population. Catalysis is also used in the production of plastics, which are used in countless products from packaging to automobiles. The development of new and improved catalysts is essential for the chemical industry to continue to meet the growing demands of the world's population. The Haber-Bosch process, a cornerstone of modern agriculture, exemplifies the transformative power of catalysis. Developed in the early 20th century by German chemists Fritz Haber and Karl Bosch, this process enables the direct synthesis of ammonia from nitrogen and hydrogen gases using an iron-based catalyst. Prior to this invention, obtaining usable nitrogen for fertilizers was a major challenge, severely limiting agricultural productivity. The Haber-Bosch process revolutionized agriculture by providing a readily available source of nitrogen fertilizer, leading to dramatic increases in crop yields and supporting the growth of the global population. However, this process also has its drawbacks. It is energy intensive, requiring high temperatures and pressures, and it relies on fossil fuels as a source of hydrogen. Researchers are now working to develop more sustainable methods for ammonia production, such as using renewable energy sources and exploring alternative catalysts. The story of the Haber-Bosch process is a testament to the power of human ingenuity and the importance of catalysis in addressing global challenges. Catalysis plays a crucial role in the development of sustainable technologies. As we face growing environmental challenges, such as climate change and pollution, the need for cleaner and more efficient chemical processes is becoming increasingly urgent. Catalysts can help us to reduce waste, conserve energy, and use renewable resources more effectively. For example, catalysts are used in catalytic converters in automobiles to reduce emissions of harmful pollutants such as carbon monoxide, nitrogen oxides, and hydrocarbons. Catalysts are also used in the production of biofuels, which are renewable alternatives to fossil fuels. The development of new catalysts that can efficiently convert biomass into fuels and chemicals is a major area of research. Imagine a future where all of our energy and materials are produced using sustainable chemical processes powered by catalysts. This is the vision that drives many researchers in the field of catalysis. Consider the intricate design of a catalytic converter in your car, a silent guardian against harmful emissions. This device utilizes a variety of catalysts, typically precious metals like platinum, palladium, and rhodium, to convert toxic gases into less harmful substances. As exhaust gases flow through the catalytic converter, the catalysts facilitate reactions that oxidize carbon monoxide and hydrocarbons into carbon dioxide and water and reduce nitrogen oxides into nitrogen gas. The efficiency of a catalytic converter depends on several factors, including the temperature of the exhaust gases, the composition of the catalyst, and the flow rate of the gases. The development of more efficient and durable catalytic converters is an ongoing effort, driven by increasingly stringent emission standards and the need to reduce air pollution. The catalytic converter is a prime example of how catalysis can be used to address environmental challenges and improve the quality of our air. And as you drift deeper into sleep, think about the future of catalysis. Researchers are constantly developing new and improved catalysts with enhanced activity, selectivity, and stability. Nanotechnology is playing an increasingly important role in catalyst design, allowing chemists to create catalysts with precisely controlled structures and properties. The use of computational methods is also accelerating the discovery of new catalysts by allowing researchers to simulate chemical reactions and predict the performance of different catalysts. The future of catalysis is bright, with the potential to revolutionize many industries and solve some of the world's most pressing challenges. Imagine a future where catalysts are used to capture carbon dioxide from the atmosphere and convert it into valuable products, or where catalysts are used to produce clean and affordable energy from renewable resources. The possibilities are endless. Nanotechnology offers unprecedented opportunities for designing catalysts with enhanced performance and unique properties. By manipulating materials at the nanoscale, researchers can create catalysts with increased surface area, tailored pore sizes, and precisely controlled compositions. Nanoparticles, nanowires, and nanotubes can all be used as building blocks for catalysts, allowing chemists to fine-tune their catalytic activity and selectivity. For example, nanoparticles of gold, which are inert in bulk form, can become highly active catalysts when dispersed on a support material. The unique electronic and structural properties of nanomaterials make them ideal for a wide range of catalytic applications, from chemical synthesis to environmental remediation. The development of nanotechnology-based catalysts is a rapidly growing field with the potential to transform many industries. The integration of computational methods into catalyst design has revolutionized the field, allowing researchers to predict and optimize the performance of catalysts before they are even synthesized. Using quantum mechanics and molecular dynamic simulations, chemists can model chemical reactions at the atomic level and understand how catalysts interact with reactants. These simulations can provide valuable insights into the reaction mechanism, the active site structure, and the electronic properties of the catalyst. By screening a large number of potential catalyst candidates computationally, researchers can identify the most promising ones for experimental testing, significantly accelerating the discovery process. Computational catalysis is becoming an increasingly important tool for the development of new and improved catalysts. And as you continue to relax, let your mind wander to the fundamental principles that govern catalysis. Catalysis is not just about accelerating reactions. It's about understanding the underlying chemical processes that determine reaction rates and selectivity. Catalysts work by lowering the activation energy of a reaction, which is the energy barrier that must be overcome for the reaction to occur. This is achieved by providing an alternative reaction pathway with a lower activation energy. Catalysts also stabilize the transition state, which is the highest energy point along the reaction pathway. By lowering the activation energy and stabilizing the transition state, catalysts can significantly accelerate reaction rates. Understanding these fundamental principles is essential for designing new and improved catalysts. The concept of activation energy is central to understanding how catalysts work. Imagine a ball sitting at the bottom of a hill. To get the ball to the other side, you need to push it over the hill. The height of the hill represents the activation energy of the reaction. A catalyst acts like a tunnel through the hill, providing an easier pathway for the ball to reach the other side. By lowering the activation energy, the catalyst makes it easier for the reaction to occur, significantly increasing the reaction rate. The activation energy is a fundamental property of a chemical reaction that determines how fast it will proceed. The transition state is a fleeting, high-energy state that molecules must pass through during a chemical reaction. It represents the point of maximum energy along the reaction pathway, where bonds are breaking and forming. Catalysts stabilize the transition state by interacting with the reacting molecules and lowering its energy. This stabilization reduces the overall activation energy of the reaction, making it easier for the reaction to occur. The transition state is a crucial concept in understanding how catalysts work and is often the target of catalyst design efforts. And as you approach sleep, think about the different types of catalysts. Catalysts can be broadly classified into two categories: homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are soluble in the reaction mixture, while heterogeneous catalysts are insoluble. Each type of catalyst has its own advantages and disadvantages. Homogeneous catalysts are typically more active and selective than heterogeneous catalysts, but they can be difficult to separate from the reaction products. Heterogeneous catalysts are easier to separate from the reaction products, but they may be less active and selective. The choice of catalyst depends on the specific reaction and the desired outcome. Homogeneous catalysts, dissolving seamlessly into the reaction mixture, offer a unique level of control and precision. Because they're in the same phase as the reactants, they can interact intimately with the molecules involved, leading to high activity and selectivity. Imagine a skilled dancer leading their partner with grace and precision. That's how a homogeneous catalyst guides a reaction. However, this intimate interaction also presents a challenge. Separating the catalyst from the products can be difficult, requiring sophisticated techniques. Despite this challenge, homogeneous catalysis remains a powerful tool in chemical synthesis, particularly for creating complex molecules with high purity. Heterogeneous catalysts, existing as a separate phase from the reactants, offer the advantage of easy separation and reuse. Think of them as sturdy, reliable workhorses, providing a solid surface on which reactions can occur. The reactants adsorb onto the surface of the catalyst, where they interact and form products, which then door back into the reaction mixture. The catalyst itself remains unchanged, ready to catalyze another round of reactions. This ease of separation makes heterogeneous catalysts ideal for large-scale industrial processes, where cost-effectiveness and sustainability are paramount. From catalytic converters in cars to the production of ammonia, heterogeneous catalysts play a vital role in our modern world. And as you continue to relax, consider the environmental impact of catalysis. Catalysis can play a crucial role in reducing pollution and promoting sustainable chemistry. By developing catalysts that are more efficient, selective, and durable, we can reduce waste, conserve energy, and minimize the use of hazardous materials. Catalysis is also essential for the development of renewable energy technologies, such as solar cells and fuel cells. The future of catalysis is closely linked to the future of our planet. The principles of green chemistry are closely aligned with the goals of catalysis. Green chemistry seeks to design chemical processes that are environmentally benign, minimizing waste, reducing the use of hazardous materials, and conserving energy. Catalysis plays a central role in green chemistry by enabling more efficient and selective reactions, reducing the need for stoichiometric reagents and harsh reaction conditions. By using catalysts, we can design chemical processes that are both economically viable and environmentally sustainable. The development of green catalysts is a major area of research, with the goal of creating catalysts that are non-toxic, biodegradable, and derived from renewable resources. Imagine a world where chemical processes are designed with the environment in mind, where waste is minimized and resources are used efficiently. This is the vision of green chemistry, and catalysis is a key enabler. By developing catalysts that can selectively convert waste products into valuable chemicals, we can close the loop and create a circular economy. Catalysts can also be used to replace toxic reagents with safer alternatives, reducing the risk of accidents and environmental contamination. The principles of green chemistry and catalysis are essential for creating a sustainable future. And as you drift further into sleep, think about the challenges and opportunities in the field of catalysis. Despite the remarkable progress that has been made, there are still many challenges to overcome. One of the biggest challenges is the design of catalysts that are both active and selective. It is often difficult to find a catalyst that can accelerate a reaction without also producing unwanted side products. Another challenge is the development of catalysts that are stable under harsh reaction conditions. Many catalysts deactivate over time due to poisoning, sintering, or leaching. Overcoming these challenges will require a deeper understanding of the fundamental principles of catalysis and the development of new and innovative catalyst design strategies. The quest for the perfect catalyst, one that is both highly active and exquisitely selective, is a driving force behind much of the research in catalysis. Imagine a catalyst that can selectively convert a complex mixture of reactants into a single desired product with minimal waste. This would revolutionize chemical synthesis, allowing us to produce pharmaceuticals, materials, and fuels with unprecedented efficiency and precision. Achieving this level of control requires a deep understanding of the reaction mechanism and the ability to tailor the catalyst structure and properties to precisely match the requirements of the reaction. The pursuit of the perfect catalyst is a challenging but rewarding endeavor that has the potential to transform our world. The stability of catalysts under harsh reaction conditions is a critical factor in their practical application. Many industrial processes involve high temperatures, pressures, and corrosive environments, which can lead to catalyst deactivation. Catalyst deactivation can occur through a variety of mechanisms, including poisoning, where impurities in the reaction mixture bind to the active sites of the catalyst, blocking their activity, sintering, where the catalyst particles agglomerate, reducing the surface area available for reaction, and leaching, where the active components of the catalyst dissolve into the reaction mixture. Developing catalysts that are resistant to these deactivation mechanisms is essential for ensuring their long-term performance and economic viability. And as you continue to relax, let your thoughts turn to the future applications of catalysis. Catalysis has the potential to play a crucial role in addressing some of the world's most pressing challenges, such as climate change, energy security, and food security. Catalysts can be used to capture carbon dioxide from the atmosphere and convert it into valuable products, to produce clean and affordable energy from renewable resources, and to improve the efficiency of agriculture. The future of catalysis is bright, with the potential to revolutionize many industries and create a more sustainable world. Imagine a future where carbon dioxide, a major greenhouse gas, is no longer a waste product but a valuable resource. Catalysis can play a key role in realizing this vision by enabling the conversion of carbon dioxide into fuels, chemicals, and materials. For example, carbon dioxide can be reacted with hydrogen to produce methane, a fuel that can be used to generate electricity or power vehicles. Carbon dioxide can also be used to produce plastics, polymers, and other valuable chemicals. The development of efficient and selective catalysts for carbon dioxide conversion is a major area of research, with the potential to mitigate climate change and create a more sustainable economy. Catalysis is essential for the development of clean and affordable energy from renewable resources. Solar cells use catalysts to convert sunlight into electricity, while fuel cells use catalysts to convert fuels into electricity with high efficiency and low emissions. Catalysts are also used in the production of biofuels, which are renewable alternatives to fossil fuels. The development of new and improved catalysts for renewable energy technologies is crucial for ensuring a sustainable energy future. And as you drift closer to sleep, remember the remarkable impact that catalysis has had on our lives. From the medicines that keep us healthy to the materials that build our homes, catalysts have played a vital role in shaping the modern world. They are the unseen catalysts of progress, silently and efficiently transforming the world around us. So, close your eyes and imagine the intricate dance of atoms and electrons, the silent symphony of chemical reactions, and the endless possibilities of catalysis. May your dreams be filled with the wonders of science and the promise of a brighter future. Consider the profound impact of catalysis on the pharmaceutical industry. Many life-saving drugs are synthesized using catalytic reactions, enabling the efficient and selective production of complex molecules. Catalysts can be used to reduce the number of steps required to synthesize a drug, lower production costs, and minimize waste. The development of new and improved catalysts for pharmaceutical synthesis is an ongoing effort, driven by the need to produce drugs that are more effective, less toxic, and more affordable. The synthesis of complex molecules, the building blocks of life and the foundation of modern medicine, often relies on the power of catalysis. Imagine trying to construct an intricate Lego model without instructions or tools. That's akin to synthesizing a complex molecule without a catalyst. Catalysts act as molecular guides, directing the assembly of atoms and bonds with precision and efficiency. They can accelerate reactions, reduce unwanted side products, and enable the creation of molecules that would otherwise be impossible to synthesize. From the development of new drugs to the creation of advanced materials, catalysis is an indispensable tool for chemists and engineers. And as you finally succumb to sleep, let the quiet hum of chemical reactions soothe you. Think of the billions of catalysts working tirelessly around the world, in laboratories, factories, and even within your own body. They are the unsung heroes of chemistry, the silent orchestrators of molecular transformations. They are a testament to the power of human ingenuity and the beauty of science. Sleep well, knowing that the world of catalysis is constantly evolving, with new discoveries and innovations on the horizon. The elegance of catalysis lies not only in its practical applications, but also in its fundamental scientific principles. Understanding how catalysts work requires a deep understanding of chemical kinetics, thermodynamics, and quantum mechanics. It is a multidisciplinary field that brings together chemists, physicists, and engineers to solve complex problems and create new technologies. The study of catalysis is not just about making new molecules. It's about understanding the fundamental laws of nature and using them to our advantage. It's about harnessing the power of chemistry to create a better world. Chemical kinetics, the study of reaction rates and mechanisms, is essential for understanding how catalysts accelerate reactions. By measuring the rate of a reaction in the presence and absence of a catalyst, we can determine the catalyst's effectiveness and identify the rate-determining step of the reaction. This information is crucial for designing catalysts that can further accelerate the reaction and improve its selectivity. Chemical kinetics provides the framework for understanding how catalysts work at a molecular level. Thermodynamics, the study of energy and its transformations, provides insights into the feasibility of a chemical reaction. A reaction is thermodynamically favorable if it releases energy, exothermic, and increases entropy, disorder. However, even if a reaction is thermodynamically favorable, it may not occur at a measurable rate without a catalyst. Catalysts do not change the thermodynamics of a reaction. They only accelerate the rate at which it reaches equilibrium. Understanding the thermodynamics of a reaction is essential for selecting the appropriate catalyst and reaction conditions. Quantum mechanics, the theory that describes the behavior of matter at the atomic and subatomic level, provides the most fundamental understanding of catalysis. Catalytic reactions involve the breaking and forming of chemical bonds, which are governed by the laws of quantum mechanics. By using quantum mechanical calculations, we can model the electronic structure of catalysts and reactants and predict their reactivity. Quantum mechanics is becoming an increasingly important tool for catalyst design, allowing researchers to develop catalysts with tailored properties. And now, as you are sound asleep, let the image of catalysts, those tireless molecular machines, stay with you. They are a symbol of human ingenuity and the boundless potential of science. Sweet dreams, filled with the wonders of the chemical world. The elegance of catalysis extends far beyond the laboratory bench. Consider, for instance, the Haber-Bosch process, a catalytic reaction that transformed agriculture in the 20th century. This process, which utilizes an iron-based catalyst to convert atmospheric nitrogen and hydrogen into ammonia, revolutionized fertilizer production. Before Haber-Bosch, farmers relied primarily on natural sources of nitrogen, such as manure and guano, which were often scarce and inefficient. The Haber-Bosch process provided a virtually limitless supply of nitrogen fertilizer, enabling farmers to dramatically increase crop yields and feed a rapidly growing global population. However, this seemingly miraculous process is not without its drawbacks. The widespread use of nitrogen fertilizers has led to environmental problems such as water pollution and greenhouse gas emissions. This highlights the complex interplay between scientific innovation and its consequences, reminding us that even the most beneficial technologies can have unintended impacts. The story of Haber-Bosch serves as a potent reminder of the double-edged sword of scientific advancement, a constant balancing act between progress and potential peril. It also underscores the crucial role of chemists in developing sustainable and environmentally friendly alternatives to current industrial processes. Imagine the intricate dance of molecules on the surface of a catalyst, a microscopic ballet orchestrated by the laws of physics and chemistry. The catalyst acts as a stage, bringing reactants together in the optimal orientation for reaction. It's like a dating service for molecules, facilitating encounters that would otherwise be unlikely. The catalyst lowers the activation energy of the reaction, the energy barrier that must be overcome for the reaction to proceed. Think of it as digging a tunnel through a mountain instead of climbing over it. The tunnel allows you to reach the other side with less effort, and the catalyst allows the reaction to proceed more quickly and efficiently. The beauty of this process is that the catalyst is not consumed in the reaction. It emerges unchanged, ready to catalyze another reaction. It's like a master chef who can prepare countless meals without ever running out of ingredients. The catalyst simply facilitates the transformation, guiding the reactants along the path to product formation. The history of catalysis is rich with stories of serendipitous discoveries and brilliant insights. One of the earliest examples of catalysis was the discovery of enzymatic catalysis by Anselm Payen in 1833. Payen observed that an extract of malt could convert starch into sugar, a process he attributed to a mysterious substance he called diastase, now known as amylase. This discovery laid the foundation for the field of enzymology and paved the way for the development of industrial processes based on enzymatic catalysis. Later, in the late 19th and early 20th centuries, chemists such as Wilhelm Ostwald and Paul Sabatier made significant contributions to the understanding of heterogeneous catalysis, the type of catalysis in which the catalyst and reactants are in different phases. Ostwald's work on the catalytic oxidation of ammonia led to the development of the Ostwald process, a crucial step in the production of nitric acid, an important ingredient in fertilizers and explosives. Sabatier's research on the hydrogenation of organic compounds using metal catalysts opened up new avenues for the synthesis of a wide range of chemicals, including margarine. These early pioneers of catalysis laid the groundwork for the sophisticated catalytic technologies we use today. Consider the analogy of a lock and key to understand the specificity of enzymes. Enzymes are biological catalysts that exhibit remarkable selectivity, catalyzing only specific reactions involving specific substrates. This selectivity arises from the precise fit between the enzyme's active site and the substrate molecule. The active site is a three-dimensional pocket within the enzyme molecule that is complementary in shape and chemical properties to the substrate. Just as a key can only unlock a specific lock, a substrate can only bind to a specific enzyme. This locking key mechanism ensures that enzymes catalyze only the reactions for which they are designed, preventing unwanted side reactions and ensuring the efficient functioning of biological systems. The locking key analogy, while useful, is an oversimplification. In reality, the enzyme and substrate undergo conformational changes upon binding, a process known as induced fit. The enzyme molds itself around the substrate, optimizing the interaction and facilitating the catalytic reaction. This dynamic interaction between enzyme and substrate is crucial for enzyme function and highlights the complexity of biological catalysis. The development of new catalysts is a constant quest, driven by the desire to create more efficient, selective, and sustainable chemical processes. One of the most exciting areas of research in catalysis is the development of homogeneous catalysts that are soluble in the same phase as the reactants. Homogeneous catalysts offer several advantages over heterogeneous catalysts, including higher activity and selectivity. However, homogeneous catalysts can be difficult to recover and reuse, which limits their industrial applicability. Researchers are developing new strategies to overcome this limitation, such as immobilizing homogeneous catalysts on solid supports or using biphasic systems in which the catalyst is dissolved in one phase and the reactants and products are dissolved in another. Another promising area of research is the development of biocatalysts, enzymes, or whole cells that can be used to catalyze chemical reactions. Biocatalysts are often highly selective and can operate under mild conditions, making them attractive for the synthesis of pharmaceuticals and other fine chemicals. The future of catalysis is bright, with new discoveries and innovations constantly emerging. Imagine the intricate network of chemical reactions occurring within your own body, all orchestrated by enzymes. Enzymes are the catalysts of life, responsible for virtually every biochemical reaction that takes place in cells. They catalyze the digestion of food, the synthesis of DNA, the transport of oxygen, and countless other essential processes. Without enzymes, life as we know would not be possible. Each enzyme is a highly specialized protein that catalyzes a specific reaction. The human body contains thousands of different enzymes, each with its unique function. These enzymes work together in a complex and coordinated manner to maintain the delicate balance of life. The study of enzymes is a fascinating field that has revolutionized our understanding of biology and medicine. By understanding how enzymes work, we can develop new drugs to treat diseases and improve human health. The impact of catalysis on the pharmaceutical industry is profound. Many of the drugs we rely on today are synthesized using catalytic reactions. Catalysis enables the efficient and selective synthesis of complex molecules, reducing the cost and environmental impact of drug production. For example, the synthesis of many chiral drugs that exist as two mirror image isomers, relies on asymmetric catalysis, a type of catalysis that selectively produces one isomer over the other. Asymmetric catalysis is essential for the synthesis of chiral drugs because the two isomers can have different biological activities, with one isomer being therapeutic and the other being inactive or even toxic. The development of new asymmetric catalysts has revolutionized the pharmaceutical industry, enabling the synthesis of a wide range of chiral drugs with high purity and efficacy. Catalysis is also playing an increasingly important role in the development of new drug delivery systems, such as nanoparticles that can target drugs directly to cancer cells. Think of the catalytic converter in your car, a device that reduces the emissions of harmful pollutants from the exhaust. The catalytic converter uses a combination of metal catalysts, typically platinum, palladium, and rhodium, to convert carbon monoxide, hydrocarbons, and nitrogen oxides into carbon dioxide, water, and nitrogen. These catalysts accelerate the oxidation of carbon monoxide and hydrocarbons and the reduction of nitrogen oxides, converting them into less harmful substances. Catalytic converters have significantly reduced air pollution in urban areas, improving public health and protecting the environment. The development of catalytic converters is a testament to the power of catalysis to solve environmental problems. However, catalytic converters are not without their limitations. They are expensive, require the use of precious metals, and can be poisoned by lead and sulfur. Researchers are developing new and improved catalytic converters that are more efficient, durable, and environmentally friendly. The ongoing quest for new and improved catalysts is fueled by a desire to address some of the world's most pressing challenges, from climate change to disease. Catalysis is playing a crucial role in the development of sustainable energy technologies, such as fuel cells and solar cells. Fuel cells use catalysts to convert fuels, such as hydrogen or methane, into electricity and water. Solar cells use catalysts to convert sunlight into electricity. Catalysis is also essential for the development of new materials with enhanced properties, such as stronger, lighter, and more durable plastics. These new materials can be used in a wide range of applications, from aerospace to construction. The potential of catalysis to transform our world is limitless. As we continue to unlock the secrets of catalysis, we can expect to see even more remarkable innovations in the years to come. Now, let your mind drift back to the microscopic world, to the bustling activity on the surface of a catalyst. Imagine the relentless dance of molecules, the breaking and forming of bonds, the constant transformation of matter. These catalysts, these tireless molecular machines, are working day and night to create the products we need and improve our lives. They are the unsung heroes of chemistry, the silent orchestrators of molecular transformations. They are a testament to the power of human ingenuity and the beauty of science. Allow these thoughts to gently carry you into a peaceful slumber, knowing that the world of catalysis is constantly evolving, with new discoveries and innovations on the horizon. As you drift off to sleep, remember the intricate processes happening at a molecular level, the reactions that sustain life and drive progress. Consider the synthesis of ammonia through the Haber-Bosch process as a prime example of heterogeneous catalysis. In this process, nitrogen and hydrogen gases react on the surface of an iron catalyst to form ammonia. The iron catalyst provides a surface where the nitrogen and hydrogen molecules can adsorb and dissociate, weakening the strong triple bond of nitrogen and allowing it to react with hydrogen. The reaction proceeds through a series of steps, with the catalyst facilitating each step. The iron catalyst is not consumed in the reaction, but it plays a crucial role in lowering the activation energy and accelerating the reaction rate. The Haber-Bosch process has revolutionized agriculture, but it also has significant environmental consequences, highlighting the need for more sustainable catalytic processes. The process itself takes place at high temperatures and pressures, requiring significant energy input. Future research aims to develop catalysts that can operate under milder conditions and utilize renewable energy sources. The concept of green chemistry is closely intertwined with catalysis. Green chemistry seeks to design chemical products and processes that minimize or eliminate the use and generation of hazardous substances. Catalysis plays a crucial role in green chemistry by enabling the development of more efficient and selective reactions that produce less waste and require less energy. For example, the use of biocatalysts, such as enzymes, can often replace traditional chemical catalysts, reducing the need for harsh reaction conditions and toxic solvents. Catalysis can also be used to develop new chemical processes that utilize renewable feedstocks, such as biomass, instead of fossil fuels. The principles of green chemistry are guiding the development of new catalytic technologies that are both environmentally friendly and economically viable. The adoption of green chemistry principles is essential for creating a more sustainable future. Think about the use of zeolites as catalysts in the petroleum industry. Zeolites are crystalline aluminosilicates with a porous structure that allows them to act as shape-selective catalysts. The pores of a zeolite can selectively adsorb and react molecules based on their size and shape. This shape selectivity makes zeolites ideal catalysts for cracking large hydrocarbon molecules into smaller, more valuable molecules, such as gasoline and diesel fuel. Zeolites are also used as catalysts in a variety of other industrial processes, including the synthesis of chemicals and the removal of pollutants from exhaust gases. The versatility of zeolites as catalysts stems from their tunable pore size and acidity, which can be tailored to specific applications. The development of new and improved zeolites is an ongoing area of research, with the goal of creating catalysts that are more efficient, selective, and durable. Let your thoughts meander to the realm of photocatalysis, a process in which light is used to activate a catalyst. Photocatalysts Typically, semiconductor materials such as titanium dioxide absorb light and generate electron-hole pairs, which can then drive chemical reactions. Photocatalysis has a wide range of applications, including water purification, air purification, and solar energy conversion. For example, photocatalysis can be used to break down organic pollutants in water, such as pesticides and dyes, into harmless substances. Photocatalysis can also be used to generate hydrogen from water, a clean and sustainable energy source. The efficiency of photocatalytic processes depends on the properties of the photocatalyst, such as its band gap, surface area, and charge carrier mobility. Researchers are developing new and improved photocatalysts with enhanced activity and stability. The study of catalysis is not just about understanding how catalysts work. It's also about designing new catalysts with tailored properties. Catalyst design is a complex process that involves understanding the relationship between the catalyst structure and its activity. Researchers use a variety of techniques to design new catalysts, including computational modeling, high-throughput screening, and combinatorial chemistry. Computational modeling allows researchers to simulate the behavior of catalysts at the atomic level, providing insights into the reaction mechanism and identifying potential improvements to the catalyst structure. High-throughput screening allows researchers to rapidly test the activity of a large number of catalysts, identifying the most promising candidates for further development. Combinatorial chemistry allows researchers to synthesize a large library of catalysts with different compositions and structures, enabling the discovery of new and unexpected catalytic activities. The role of surface science in understanding heterogeneous catalysis is paramount. Surface science provides the tools and techniques to study the structure and composition of catalyst surfaces at the atomic level. Techniques such as X-ray photoelectron spectroscopy, XPS, scanning tunneling microscopy, STM, and atomic force microscopy, AFM, can be used to characterize the surface of a catalyst, revealing information about the arrangement of atoms, the presence of defects, and the adsorption of reactants. This information is crucial for understanding how the catalyst works and for designing new and improved catalysts. Surface science has played a key role in the development of many important catalytic technologies, such as catalytic converters and fuel cells. The ongoing development of new surface science techniques is providing even deeper insights into the behavior of catalysts at the nanoscale. Imagine the impact of catalysis on the production of plastics. Many of the plastics we use today are synthesized using catalytic polymerization reactions. Catalysts allow for the efficient and selective polymerization of monomers, such as ethylene and propylene, into long chains of polymers. These polymers can then be molded into a wide variety of shapes and sizes, creating the plastics we use in everything from packaging to automobiles. The development of new and improved polymerization catalysts has revolutionized the plastics industry, enabling the production of plastics with enhanced properties such as higher strength, lower weight, and greater durability. Catalysis is also playing a role in the development of biodegradable plastics, which can be broken down by microorganisms in the environment. reducing the problem of plastic waste. As you continue to relax, consider the connection between catalysis and nanotechnology. Nanomaterials, materials with dimensions on the nanometer scale, often exhibit unique catalytic properties. The high surface area of nanomaterials allows for a greater number of active sites, leading to enhanced catalytic activity. Nanomaterials can also be designed with specific shapes and sizes to control the selectivity of catalytic reactions. For example, nanoparticles of gold, platinum, and palladium are used as catalysts in a variety of applications, including the oxidation of carbon monoxide and the reduction of nitrogen oxides. The development of new nanomaterials with tailored catalytic properties is an active area of research, with the potential to create catalysts that are more efficient, selective, and durable. The ethical considerations surrounding catalysis are becoming increasingly important. As catalysis enables the development of new technologies, it is essential to consider the potential impacts of these technologies on society and the environment. For example, the Haber-Bosch process, while revolutionizing agriculture, has also contributed to environmental problems such as water pollution and greenhouse gas emissions. It is important to develop and implement catalytic technologies in a responsible and sustainable manner, minimizing their negative impacts and maximizing their benefits. This requires a multidisciplinary approach involving chemists, engineers, policymakers, and the public. The ethical considerations surrounding catalysis are not always straightforward, but they are essential for ensuring that catalytic technologies are used for the benefit of humanity and the planet. Think about the role of catalysis in the development of new sensors. Catalytic sensors use catalysts to detect the presence of specific chemicals in the environment. For example, catalytic sensors can be used to detect the presence of toxic gases, such as carbon monoxide and nitrogen dioxide, in the air. Catalytic sensors can also be used to detect the presence of explosives, such as TNT, in the soil. The sensitivity and selectivity of catalytic sensors depend on the properties of the catalyst. Researchers are developing new and improved catalytic sensors with enhanced performance, enabling the detection of chemicals at lower concentrations and with greater accuracy. Catalytic sensors are playing an increasingly important role in environmental monitoring, homeland security, and medical diagnostics. The future of catalysis is bright, with new discoveries and innovations constantly emerging. Researchers are exploring new catalytic materials, new catalytic reactions, and new catalytic processes. They are also developing new tools and techniques for studying and designing catalysts. The ongoing quest for new and improved catalysts is driven by a desire to address some of the world's most pressing challenges, from climate change to disease. As we continue to unlock the secrets of catalysis, we can expect to see even more remarkable innovations in the years to come. These innovations will transform our world, making it more sustainable, more prosperous, and more healthy. So as you drift off to sleep, remember the power of catalysis, the power of chemistry to transform our world. Let your mind wander to the intricate details of enzyme kinetics. Enzyme kinetics is the study of the rates of enzyme-catalyzed reactions. By measuring the rate of a reaction under different conditions, such as varying the concentration of the substrate or the enzyme, we can determine the enzyme's kinetic parameters, such as its Michaelis constant, Km, and its maximum velocity, Vmax. These parameters provide insights into the enzyme's affinity for its substrate and its catalytic efficiency. Enzyme kinetics is essential for understanding how enzymes work and for designing new drugs that target enzymes. The study of enzyme kinetics has led to the development of many important drugs, such as inhibitors of HIV protease, which are used to treat AIDS. The concept of cooperative catalysis is an intriguing area of research. Cooperative catalysis involves the use of two or more catalysts working together to catalyze a reaction. The catalyst can work in a variety of ways, such as activating different parts of the substrate or stabilizing different transition states. Cooperative catalysis can often lead to higher activity and selectivity than using a single catalyst alone. This approach mimics the way enzymes work in biological systems, where multiple enzymes often work together in a coordinated manner to catalyze complex biochemical pathways. The development of new cooperative catalytic systems is an active area of research with the potential to create catalysts that are more efficient and versatile. Imagine the role of computational chemistry in catalyst design. Computational chemistry uses computer simulations to model the behavior of catalysts at the atomic level. These simulations can provide insights into the reaction mechanism, the electronic structure of the catalyst, and the interactions between the catalyst and the reactants. Computational chemistry can be used to predict the activity and selectivity of catalysts, guiding the design of new and improved catalysts. The increasing power of computers and the development of new computational methods are making computational chemistry an increasingly important tool for catalyst design. Computational chemistry is helping researchers to develop catalysts that are more efficient, selective, and sustainable. As you begin to feel more relaxed, think about the importance of catalyst support materials. Catalyst support materials are used to disperse and stabilize catalysts, preventing them from agglomerating and losing their activity. Support materials can also enhance the activity and selectivity of catalysts by providing a high surface area and by modifying the electronic properties of the catalyst. Common support materials include metal oxides, such as alumina and silica, and carbon materials, such as activated carbon and carbon nanotubes. The choice of support material depends on the specific application and the properties of the catalyst. Researchers are developing new and improved support materials with enhanced properties, such as higher surface area, greater stability, and improved electronic conductivity. The concept of single-atom catalysis is a cutting-edge field. Single-atom catalysts are catalysts in which the active catalytic sites are isolated single atoms dispersed on a support material. Single-atom catalysts can exhibit unique catalytic properties due to their well-defined structure and their ability to interact strongly with the reactants. The preparation of single-atom catalysts is challenging, but recent advances in nanotechnology have made it possible to create these materials with high precision. Single-atom catalysts have shown promising results in a variety of applications, including oxidation reactions, hydrogenation reactions, and CO2 reduction. The field of single-atom catalysis is rapidly evolving, with the potential to revolutionize the way we design and use catalysts. Now, let your thoughts drift to the applications of catalysis in environmental remediation. Catalysis can be used to remove pollutants from air, water, and soil. For example, catalytic oxidation can be used to remove volatile organic compounds, VOCs, from industrial emissions. Catalytic reduction can be used to remove nitrogen oxides, NOx, from exhaust gases. Catalytic decomposition can be used to break down organic pollutants in water and soil. Catalysis is playing an increasingly important role in environmental remediation, helping to clean up our planet and protect our health. The development of new and improved catalytic technologies for environmental remediation is an ongoing effort driven by the need to address the growing environmental challenges we face. The connection between catalysis and fuel cell technology is crucial. Fuel cells use catalysts to convert fuels, such as hydrogen or methane, into electricity and water. Catalysts are used in both the anode and the cathode of the fuel cell, facilitating the oxidation of the fuel and the reduction of oxygen. The efficiency and performance of fuel cells depend critically on the properties of the catalysts. Researchers are developing new and improved catalysts for fuel cells with the goal of increasing their efficiency, reducing their cost, and improving their durability. Fuel cell technology has the potential to provide clean and sustainable energy for transportation, power generation, and other applications. As you feel yourself drifting closer to sleep, consider the importance of catalyst recycling. Catalyst recycling is the process of recovering and reusing catalysts after they have been used in a chemical reaction. Catalyst recycling is important for both economic and environmental reasons. Catalysts can be expensive, and recycling them can reduce the cost of chemical production. Catalyst recycling also reduces the amount of waste generated by chemical processes, minimizing their environmental impact. A variety of methods are used for catalyst recycling, including solvent extraction, distillation, and incineration. The choice of method depends on the type of catalyst and the nature of the waste stream. The development of new and improved catalyst recycling technologies is an ongoing effort driven by the desire to make chemical processes more sustainable. The use of ionic liquids as catalysts or catalyst supports is an area of growing interest. Ionic liquids are salts that are liquid at or near room temperature. They have unique properties such as low volatility, high ionic conductivity, and good solubility for a wide range of compounds. Ionic liquids can be used as catalysts in a variety of chemical reactions, including alkylation, acylation, and polymerization. They can also be used as catalyst supports, providing a stable and recyclable medium for catalysts. The use of ionic liquids in catalysis can lead to more efficient, selective, and environmentally friendly chemical processes. The development of new and improved ionic liquids for catalysis is an active area of research. Finally, as you prepare to enter a state of deep and restful sleep, Let the image of catalysts, those tireless molecular machines, stay with you. They are a symbol of human ingenuity and the boundless potential of science. They are a reminder that even the smallest things can have a profound impact on the world. Sweet dreams, filled with the wonders of the chemical world. And remember, even in your dreams, the catalysts are still working silently and tirelessly to make the world a better place. Sleep soundly, knowing that the future of catalysis is bright and that the possibilities are endless. Now, let's delve a little deeper into the fascinating world of enzyme catalysis. Enzymes, as you might know, are biological catalysts, primarily proteins, that accelerate biochemical reactions within living organisms. Their catalytic power is truly remarkable, often exceeding that of synthetic catalysts by many orders of magnitude. This efficiency stems from their highly specific three-dimensional structures, which create an active site perfectly tailored to bind and transform a particular substrate. Think of it like a lock and key, where the enzyme, the lock, only works with a specific substrate, the key. This exquisite specificity ensures that reactions occur with minimal side products, which is crucial in biological systems where precision is paramount. The process of enzyme catalysis typically involves several steps. First, the substrate binds to the active site of the enzyme, forming an enzyme-substrate complex. This binding event is often driven by a combination of non-covalent interactions, such as hydrogen bonds, electrostatic interactions, and hydrophobic forces. Once the substrate is bound, the enzyme undergoes a conformational change, known as induced fit, which further optimizes the interaction and brings the catalytic groups into close proximity with the substrate. These catalytic groups, often amino acid side chains within the active site, then facilitate the chemical transformation of the substrate into the product. Finally, the product is released from the enzyme, and the enzyme returns to its original conformation, ready to catalyze another reaction. One of the most well-studied examples of enzyme catalysis is the hydrolysis of peptide bonds by enzymes called proteases. Proteases play a critical role in protein turnover, digestion, and various signaling pathways. They employ a variety of catalytic mechanisms, including acid-base catalysis, covalent catalysis, and metal ion catalysis to cleave the peptide bond. For instance, serine proteases, such as trypsin and chymotrypsin, utilize a catalytic triad consisting of serine, histidine, and aspartic acid residues to activate a water molecule, which then attacks the carbonyl carbon of the peptide bond, leading to its cleavage. The precise arrangement and interaction of these amino acids within the active site are essential for the enzyme's catalytic activity. The study of enzyme mechanisms has not only provided insights into the fundamental principles of catalysis, but also paved the way for the development of enzyme inhibitors as drugs. Many pharmaceutical drugs target specific enzymes involved in disease pathways, effectively blocking their activity and alleviating symptoms. Now, let's consider the role of catalysts in polymerization reactions, which are fundamental to the production of plastics, synthetic fibers, and many other materials we use daily. Polymerization is the process of joining small molecules, called monomers, to form large, chain-like molecules called polymers. Catalysts play a crucial role in controlling the rate, selectivity, and stereochemistry of these reactions. For example, Ziegler-Natta catalysts, discovered in the 1950s, revolutionized the production of polyethylene and polypropylene. These catalysts, typically based on titanium or zirconium compounds, allow for the polymerization of olefins with high stereoregularity, resulting in polymers with improved mechanical properties and thermal stability. The discovery of Ziegler-Natta catalysts earned Carl Ziegler and Giulio Natta the Nobel Prize in Chemistry in 1963, highlighting the profound impact of catalysis on materials science. The mechanism of Ziegler-Natta catalysis involves the coordination of the olefin monomer to the metal center of the catalyst, followed by insertion of the monomer into the growing polymer chain. The stereochemistry of the insertion is controlled by the chiral environment around the metal center, which dictates the orientation of the incoming monomer. By carefully tuning the structure of the catalyst, chemists can tailor the properties of the resulting polymer. For example, metallocene catalysts, a more recent class of polymerization catalysts, offer even greater control over polymer microstructure and allow for the synthesis of polymers with narrow molecular weight distributions and precisely defined architectures. These advances have led to the development of new and improved materials with a wide range of applications, from high-performance plastics to biomedical implants. Consider, for instance, the production of biodegradable polymers. As environmental concerns grow, there is increasing demand for sustainable materials that can decompose naturally after use. Catalysis plays a key role in the synthesis of biodegradable polymers, such as polylactic acid, PLA, which is derived from renewable resources like cornstarch. PLA can be synthesized by the ring-opening polymerization of lactide, a cyclic ester. Catalysts, such as tin, 2-octoate, are used to initiate and control the polymerization, ensuring high yields and molecular weights. PLA is biodegradable under composting conditions, breaking down into harmless substances like carbon dioxide and water. It is used in a variety of applications, including packaging, textiles, and medical devices. The development of new and improved catalysts for PLA synthesis is an ongoing area of research, driven by the desire to make the production of biodegradable polymers more efficient and cost-effective. Now, let's shift our focus to the application of catalysts in the pharmaceutical industry, specifically in the synthesis of complex organic molecules. The synthesis of pharmaceuticals often involves multiple steps, each requiring careful control of reaction conditions and selectivity. Catalysts play a vital role in streamlining these processes, reducing waste, and improving yields. For example, asymmetric catalysis, which involves the use of chiral catalysts to selectively produce one enantiomer of a chiral molecule, is essential for the synthesis of many pharmaceuticals. Enantiomers are mirror images of each other, and they can have drastically different biological activities. Therefore, it is crucial to synthesize pharmaceuticals in enantiomerically pure form. Chiral catalysts, such as chiral metal complexes and enzymes, can selectively catalyze the formation of one enantiomer over the other. The design and synthesis of effective chiral catalysts is a challenging but rewarding endeavor, as it can significantly reduce the cost and complexity of pharmaceutical synthesis. For instance, the synthesis of the anti-inflammatory drug naproxen, which contains a chiral center, has been significantly improved by the use of chiral catalysts. The original synthesis of naproxen required multiple steps and produced a racemic mixture, equal amounts of both enantiomers, which then had to be separated. However, by using a chiral catalyst, chemists can now synthesize naproxen in enantiomerically pure form in a single step, significantly reducing waste and improving efficiency. This exemplifies how advancements in catalysis directly translate to better, more efficient drug manufacturing processes. Another important application of catalysts in the pharmaceutical industry is in the development of new and improved synthetic routes for existing drugs. As patents expire and generic versions of drugs become available, pharmaceutical companies are constantly seeking ways to reduce the cost of manufacturing and improve the efficiency of their processes. Catalysis can play a key role in achieving these goals. For example, by using a more efficient catalyst, chemists can reduce the number of steps in a synthetic route, lower the reaction temperature, or use less toxic reagents. These improvements can lead to significant cost savings and environmental benefits. The ongoing research and development in catalysis ensures that the pharmaceutical industry continues to innovate and improve its manufacturing processes, ultimately benefiting patients by making drugs more affordable and accessible. Now, let's turn our attention to the role of catalysts in environmental remediation. Catalysts can be used to remove pollutants from air and water, helping to protect the environment and human health. For example, catalytic converters in automobiles use catalysts to convert harmful emissions, such as carbon monoxide, nitrogen oxides, and hydrocarbons, into less harmful substances, such as carbon dioxide, nitrogen, and water. The catalysts in catalytic converters are typically made of platinum, palladium, and rhodium, which are supported on a ceramic substrate. These metals catalyze the oxidation of carbon monoxide and hydrocarbons and the reduction of nitrogen oxides. Catalytic converters have been instrumental in reducing air pollution from automobiles, especially in urban areas. The development of more efficient and durable catalytic converters is an ongoing area of research driven by the need to meet increasingly stringent emission standards. Another important application of catalysts in environmental remediation is in the treatment of wastewater. Catalysts can be used to degrade organic pollutants in wastewater, such as pesticides, pharmaceuticals, and industrial chemicals. Advanced oxidation processes, EOPs, which involve the use of catalysts in combination with oxidants like hydrogen peroxide or ozone, are particularly effective for degrading these pollutants. For example, titanium dioxide, TiO2, is a widely used photocatalyst for wastewater treatment. When TiO2 is irradiated with ultraviolet, UV, light, it generates electron hole pairs, which can then react with water and oxygen to produce highly reactive hydroxyl radicals. These hydroxyl radicals can oxidize a wide range of organic pollutants, breaking them down into harmless substances like carbon dioxide and water. AOPs are used in a variety of wastewater treatment plants to remove recalcitrant pollutants that are not effectively removed by conventional treatment methods. The development of new and improved catalysts for AOPs is an active area of research with a goal of making wastewater treatment more efficient and cost-effective. As you continue to relax and drift further into sleep, consider the concept of heterogeneous catalysis versus homogeneous catalysis. These are two broad categories of catalysis, distinguished by the phase of the catalyst relative to the reactants. In heterogeneous catalysis, the catalyst is in a different phase from the reactants, typically a solid catalyst in contact with liquid or gaseous reactants. The catalytic converter in your car is a prime example of heterogeneous catalysis. The solid platinum, palladium, and rhodium catalysts react with the gaseous exhaust fumes. Heterogeneous catalysts are advantageous because they can be easily separated from the reaction mixture, allowing for simple product isolation and catalyst reuse. However, heterogeneous catalysts often have lower activity and selectivity compared to homogeneous catalysts, due to the limited accessibility of the active sites on the solid surface. In contrast, homogeneous catalysis involves a catalyst that is in the same phase as the reactants, typically a catalyst dissolved in a liquid solvent. Homogeneous catalysts often exhibit higher activity and selectivity compared to heterogeneous catalysts, because the active sites are more accessible to the reactants. However, homogeneous catalysts can be difficult to separate from the reaction mixture, which can complicate product isolation and catalyst recovery. An example of homogeneous catalysis is the use of soluble metal complexes to catalyze polymerization reactions. Researchers are actively developing strategies to combine the advantages of both heterogeneous and homogeneous catalysis. One approach is to immobilize homogeneous catalysts on solid supports, creating heterogeneous catalysts with high activity and selectivity. This field, often referred to as supported homogeneous catalysis, holds great promise for the development of new and improved catalytic processes. Think about the potential of artificial enzymes, also known as artificial metalloenzymes. These are synthetic catalysts designed to mimic the structure and function of natural enzymes. While natural enzymes are incredibly efficient and selective, they can be challenging to use in industrial processes due to their sensitivity to temperature, pH, and organic solvents. Artificial enzymes offer the potential to overcome these limitations by providing robust and tunable catalysts that can operate under a wider range of conditions. Artificial enzymes typically consist of a metal complex embedded within a protein or other macromolecular scaffold. The scaffold provides a three-dimensional environment that can control the access of substrates to the metal center and influence the selectivity of the reaction. The design of effective artificial enzymes is a challenging task, requiring a deep understanding of both enzyme mechanisms and coordination chemistry. Researchers are using a variety of approaches to design artificial enzymes, including rational design, directed evolution, and computational modeling. Rational design involves using structural and mechanistic information to create catalysts with specific properties. Directed evolution involves using genetic engineering to optimize the activity and selectivity of a catalyst. Computational modeling involves using computer simulations to predict the behavior of catalysts and guide their design. The development of artificial enzymes is an exciting area of research, with the potential to revolutionize catalysis and lead to the development of new and improved chemical processes. Imagine, for example, artificial enzymes designed to break down pollutants in contaminated soil or water, or to synthesize complex pharmaceuticals with unparalleled efficiency. Now, let's consider the historical development of catalysis. The concept of catalysis dates back to the early 19th century, with the work of scientists like Johannes Jacob Berzelius, who coined the term catalysis in 1835. Berzelius observed that certain substances could accelerate chemical reactions without being consumed themselves. However, the true nature of catalysis remained a mystery for many years. In the late 19th and early 20th centuries, scientists like Wilhelm Ostwald and Paul Sabatier made significant contributions to our understanding of catalysis. Ostwald studied the kinetics of catalytic reactions and developed the concept of activation energy, which explains how catalysts lower the energy barrier for a reaction. Sabatier discovered that finely divided metals, such as nickel, could catalyze the hydrogenation of organic compounds. This discovery led to the development of the Haber-Bosch process for the synthesis of ammonia, which revolutionized agriculture and is still one of the most important industrial processes today. The Haber-Bosch process uses an iron catalyst to convert nitrogen and hydrogen into ammonia, providing a crucial source of nitrogen fertilizer for crops. The 20th century saw a rapid development in the field of catalysis, with the discovery of new catalysts and the development of new catalytic processes. The discovery of Ziegler-Natta catalysts in the 1950s revolutionized the polymer industry, while the development of enzymatic catalysis led to new and improved methods for synthesizing pharmaceuticals and other fine chemicals. Today, catalysis is a vibrant and interdisciplinary field encompassing chemistry, materials science, and engineering. Researchers are constantly developing new and improved catalysts for a wide range of applications, from energy production and environmental remediation to pharmaceutical synthesis and material science. The ongoing research and development in catalysis ensures that it will continue to play a vital role in shaping our future. As you continue to drift off to sleep, remember the vital role of catalysis in sustainable chemistry. Sustainable chemistry, also known as green chemistry, aims to design chemical processes that are environmentally friendly and minimize waste. Catalysis plays a crucial role in achieving these goals by enabling more efficient and selective reactions, reducing the need for stoichiometric reagents, and minimizing the formation of byproducts. Catalytic reactions often require lower temperatures and pressures compared to non-catalytic reactions, which reduces energy consumption. They also allow for the use of less toxic reagents and solvents, minimizing the environmental impact of chemical processes. For example, catalysts can be used to replace toxic stoichiometric reagents with more benign alternatives. Stoichiometric reagents are substances that are consumed in a chemical reaction in a fixed ratio to the reactants. Many stoichiometric reagents are toxic or hazardous, posing a risk to human health and the environment. Catalysts can enable reactions to proceed with catalytic amounts of reagents, minimizing the amount of waste generated. Catalysis is also essential for the development of biorefineries, which aim to produce fuels and chemicals from renewable biomass. Biorefineries use enzymes and other catalysts to convert biomass into valuable products, reducing our reliance on fossil fuels and promoting a more sustainable economy. The development of new and improved catalysts for sustainable chemistry is an ongoing effort, driven by the need to address the growing environmental challenges we face. Consider the future of catalysis, a future brimming with possibilities. Nanocatalysis, for example, is an emerging field that involves the use of nanomaterials as catalysts. Nanomaterials, such as nanoparticles, nanowires, and nanotubes, have unique properties that make them attractive as catalysts. They have a high surface area, which provides more active sites for reactions to occur. They also exhibit quantum effects that can enhance their catalytic activity. Nanocatalysts can be used in a variety of applications, including energy production, environmental remediation, and chemical synthesis. For example, nanoparticles of gold, platinum, and palladium have been shown to be highly effective catalysts for a range of reactions. The synthesis and characterization of nanocatalysts is an active area of research. Researchers are developing new methods for controlling the size, shape, and composition of nanomaterials, allowing them to tailor their catalytic properties. They are also using advanced characterization techniques, such as electron microscopy and X-ray spectroscopy, to study the structure and reactivity of nanocatalysts. The development of nanocatalysis holds great promise for the development of new and improved catalytic processes. Imagine, for example, nanocatalysts designed to selectively convert carbon dioxide into valuable fuels and chemicals, or to efficiently remove pollutants from air and water. The possibilities are endless. Another exciting area of research is in the development of self-healing catalysts. Catalysts can often deactivate over time due to poisoning or fouling. Self-healing catalysts are designed to repair themselves, extending their lifetime and reducing the need for replacement. One approach to creating self-healing catalysts is to encapsulate the catalyst within a protective shell that can release healing agents when the catalyst is damaged. These healing agents can then repair the catalyst, restoring its activity. The development of self-healing catalysts is a challenging but rewarding endeavor, as it can significantly reduce the cost and environmental impact of catalytic processes. As you approach the final stages of sleep, think about the concept of dynamic catalysis. Dynamic catalysis involves the use of catalysts that can adapt to changing reaction conditions. These catalysts can respond to changes in temperature, pressure, or substrate concentration, optimizing their activity and selectivity. Dynamic catalysts can be designed using a variety of approaches, including the use of stimuli-responsive materials and feedback control systems. For example, a catalyst could be designed to change its conformation in response to a change in temperature, altering its activity or selectivity. Dynamic catalysis offers the potential to develop more efficient and robust catalytic processes. As you feel yourself drifting deeper into slumber, remember the interdisciplinary nature of catalysis. Catalysis is not just a branch of chemistry. It is a field that draws upon knowledge and expertise from a wide range of disciplines, including materials science, engineering, biology, and computer science. The development of new and improved catalysts requires a collaborative effort from researchers with diverse backgrounds and perspectives. The future of catalysis will depend on the ability of scientists and engineers to work together to solve complex challenges and develop innovative solutions. So, as you finally succumb to sleep, know that the world of catalysis is active, vibrant, and essential to a sustainable future. Sleep well, knowing that the silent, unseen catalysts are working tirelessly to improve our world. From the medicines that heal us to the materials that build our lives, catalysts are the unsung heroes of modern science. Let their quiet efficiency inspire you as you drift into dreams filled with the boundless potential of chemistry. And remember, even in your sleep, the catalysts continue their work, building a brighter, healthier, and more sustainable future for all. Sweet dreams. The journey into the realm of catalysis doesn't end with a conceptual understanding of its various facets. It extends into the very fabric of our daily lives, impacting industries ranging from pharmaceuticals and energy production to environmental remediation and material science. Consider, for example, the Haber-Bosch process, a catalytic reaction that revolutionized agriculture by enabling the large-scale synthesis of ammonia-based fertilizers. This process, developed in the early 20th century, utilizes an iron catalyst to convert atmospheric nitrogen and hydrogen gas into ammonia, a crucial component for plant growth. Without the Haber-Bosch process, global food production would be significantly limited, and feeding the world's population would be an even greater challenge. This seemingly simple catalytic reaction has had a profound and lasting impact on human civilization, highlighting the transformative power of catalysis. Another remarkable example of the impact of catalysis is in the field of petroleum refining. Catalytic cracking, a process that uses catalysts such as zeolites, is essential for breaking down large hydrocarbon molecules into smaller, more valuable components like gasoline and diesel fuel. This process allows us to extract the maximum amount of useful energy from crude oil, making it a cornerstone of the modern energy industry. The development of more efficient and selective catalysts for petroleum refining is an ongoing area of research, driven by the need to reduce energy consumption and minimize the environmental impact of fossil fuel production. Imagine the intricate dance of molecules on the surface of a catalyst, breaking and forming bonds with precision and efficiency, all orchestrated by the carefully designed properties of the catalytic material. The role of catalysis in environmental protection is also paramount. Catalytic converters in automobiles, for instance, use platinum, palladium, and rhodium catalysts to convert harmful pollutants like carbon monoxide, nitrogen oxides, and unburned hydrocarbons into less harmful substances like carbon dioxide, nitrogen, and water. This technology has significantly reduced air pollution in urban areas, improving public health and protecting the environment. The development of even more efficient and durable catalytic converters is an active area of research, driven by increasingly stringent emission standards and the desire to create cleaner and healthier cities. Think of these catalytic converters as miniature chemical factories, tirelessly working to neutralize the harmful byproducts of combustion, ensuring that the air we breathe is cleaner and safer. Beyond these well-established applications, catalysis is also playing a crucial role in the development of sustainable energy technologies. For example, catalysts are essential for the production of biofuels from renewable resources like algae and biomass. These biofuels offer a promising alternative to fossil fuels, reducing our reliance on finite resources and mitigating the effects of climate change. Catalysts are also being used to develop hydrogen fuel cells, which convert hydrogen gas into electricity with water as the only byproduct. This technology has the potential to revolutionize transportation and energy storage, creating a cleaner and more sustainable energy future. The quest for efficient and cost-effective catalysts for these applications is a major focus of research, as it holds the key to unlocking the full potential of renewable energy sources. Consider the intricate design of enzymes, nature's own catalysts. Enzymes are biological catalysts that accelerate biochemical reactions within living organisms, enabling life as we know it. These remarkable molecules are highly specific, catalyzing only a single type of reaction with incredible efficiency. Scientists are inspired by the efficiency and selectivity of enzymes and are working to develop synthetic catalysts that mimic their performance. This field, known as biomimetic catalysis, involves designing catalysts that incorporate features of enzymes, such as active sites with precisely positioned functional groups and hydrophobic pockets that enhance substrate binding. The development of biomimetic catalysts holds great promise for the development of new and improved catalytic processes for a wide range of applications. The study of catalysis also involves delving into the complex interactions between catalysts and reactants at the atomic level. Techniques like surface science and computational chemistry are used to understand how molecules bind to catalyst surfaces, how chemical bonds are broken and formed, and how the reaction proceeds. This fundamental knowledge is essential for designing catalysts with improved activity, selectivity, and stability. Imagine the intricate dance of electrons and atoms on the surface of a catalyst, as reactants transform into products through a series of carefully orchestrated steps. Understanding these fundamental processes is crucial for unlocking the full potential of catalysis and developing new technologies that can address some of the world's most pressing challenges. As you continue to relax, consider the concept of heterogeneous catalysis. Heterogeneous catalysis involves the use of catalysts that are in a different phase from the reactants. For example, a solid catalyst might be used to catalyze a reaction in the gas or liquid phase. This type of catalysis is widely used in industry because it allows for easy separation of the catalyst from the products. The catalyst can be recovered and reused, reducing waste and lowering costs. The design of heterogeneous catalysts involves careful consideration of the catalyst surface area, pore size, and chemical composition. These factors affect the catalyst's activity, selectivity, and stability. The development of new and improved heterogeneous catalysts is an ongoing area of research driven by the need for more efficient and sustainable chemical processes. Now, let's shift our focus to homogeneous catalysis. Homogeneous catalysis involves the use of catalysts that are in the same phase as the reactants. For example, a soluble catalyst might be used to catalyze a reaction in a liquid solution. Homogeneous catalysts can offer high activity and selectivity because the catalyst and reactants are intimately mixed. However, separating the catalyst from the products can be challenging. Researchers are developing new techniques to overcome this challenge, such as the use of supported homogeneous catalysts and phase transfer catalysis. The development of new and improved homogeneous catalysts is an active area of research driven by the desire to develop more efficient and selective chemical processes. As you drift further into sleep, think about the role of catalysis in the development of new materials. Catalysis is used to synthesize a wide range of materials, including polymers, plastics, and advanced ceramics. The properties of these materials can be tailored by controlling the catalytic process, allowing for the creation of materials with specific properties. For example, catalysts can be used to control the molecular weight, branching, and stereochemistry of polymers, affecting their strength, flexibility, and thermal stability. The development of new and improved catalysts for material synthesis is an ongoing area of research driven by the demand for materials with enhanced performance and sustainability. The quest for the perfect catalyst is a never-ending endeavor. Scientists are constantly searching for catalysts that are more active, more selective, more stable, and more environmentally friendly. This quest involves a combination of experimental research, theoretical modeling, and computational simulations. The development of new catalysts is often a process of trial and error. But with each new discovery, we gain a deeper understanding of the fundamental principles that govern catalysis. This knowledge allows us to design catalysts with greater precision and efficiency, pushing the boundaries of what is chemically possible. As you feel yourself getting sleepier, consider the economic impact of catalysis. Catalysis is a cornerstone of the chemical industry, enabling the production of a vast array of products that we rely on every day. The global market for catalysts is estimated to be worth billions of dollars, and it is growing rapidly. The development of new and improved catalysts can lead to significant economic benefits, creating new jobs and industries. The economic importance of catalysis underscores the need for continued investment in research and development in this field. The ethical considerations surrounding catalysis are also important to consider. Catalysis can be used to develop technologies that address some of the world's most pressing challenges, such as climate change and disease. However, it is also important to ensure that catalytic technologies are used responsibly and ethically. For example, catalysts used in the production of plastics should be designed to minimize the environmental impact of plastic waste. The development of sustainable and ethical catalytic technologies is essential for ensuring a brighter future for all. Imagine the future of catalysis. What new discoveries and innovations await us? Perhaps we will see the development of catalysts that can efficiently capture carbon dioxide from the atmosphere, converting it into valuable fuels and chemicals. Or perhaps we will see the development of catalysts that can selectively break down plastic waste into its constituent monomers, allowing for the creation of a circular economy for plastics. The possibilities are endless, and the future of catalysis is bright. As you finally drift off to sleep, remember the profound impact of catalysis on our world. From the medicines that heal us to the materials that build our lives, catalysts are the silent, unseen heroes of modern science. Let their quiet efficiency inspire you as you drift into dreams filled with the boundless potential of chemistry. And remember, even in your sleep, the catalysts continue their work, building a brighter, healthier, and more sustainable future for all. Sweet dreams. The intricate world of organic chemistry, synthesis, and catalysis is not just confined to laboratories and industrial plants. It permeates our everyday lives in ways we often fail to recognize. From the clothes we wear to the food we eat, catalysis plays a crucial, albeit often unseen, role in their production. Consider the synthesis of synthetic fibers like nylon and polyester, which are used to make a wide range of clothing items. Catalysts are essential for the polymerization reactions that create these long-chain molecules, dictating their properties such as strength, elasticity, and durability. Without catalysts, the production of these synthetic fibers would be significantly more difficult and expensive, impacting the fashion industry and our access to affordable clothing. The role of catalysis extends beyond the fashion industry to the realm of food production. Catalytic hydrogenation, a process that uses catalysts to add hydrogen atoms to unsaturated fats, is used to produce margarine and other processed foods. This process converts liquid vegetable oils into solid or semi-solid fats, improving their texture, stability, and shelf life. While concerns have been raised about the health effects of trans fats produced during partial hydrogenation, ongoing research is focused on developing catalysts that can selectively hydrogenate fats without producing these harmful byproducts. This highlights the ongoing effort to refine catalytic processes to improve both the efficiency and safety of food production. Beyond these direct applications, catalysis also plays a crucial role in the production of pharmaceuticals and other essential chemicals. The synthesis of complex organic molecules, such as those found in many drugs, often requires the use of highly selective catalysts to control the formation of specific stereoisomers. Stereoisomers are molecules with the same chemical formula but different three-dimensional arrangements of atoms, which can have drastically different biological activities. Catalysts that can selectively produce the desired stereoisomer are essential for ensuring the efficacy and safety of pharmaceuticals. The development of these catalysts is a challenging but rewarding endeavor, as it can lead to the discovery of new and improved medicines. The impact of catalysis extends beyond the synthesis of specific products to the development of more sustainable chemical processes. Catalysis can be used to reduce the amount of waste produced during chemical reactions, minimize energy consumption, and replace hazardous reagents with more environmentally friendly alternatives. For example, catalysts can be used to develop one-pot reactions, in which multiple chemical transformations are carried out sequentially in a single reaction vessel, eliminating the need for intermediate purification steps and reducing waste. Catalysis can also be used to develop reactions that operate under milder conditions, reducing energy consumption and minimizing the risk of accidents. The development of sustainable catalytic processes is essential for creating a more environmentally responsible chemical industry. The quest for new and improved catalysts is a global endeavor involving researchers from academia, industry, and government laboratories. These researchers are constantly exploring new catalytic materials, reaction mechanisms, and process designs. They are also developing new tools and techniques for characterizing catalysts and understanding their behavior at the atomic level. This collaborative effort is driving innovation in catalysis and leading to the development of new technologies that can address some of the world's most pressing challenges. As you feel your mind relaxing, consider the role of computational chemistry in catalyst design. Computational chemistry involves the use of computer simulations to model chemical reactions and predict the properties of catalysts. These simulations can provide valuable insights into the reaction mechanism, identify potential bottlenecks, and guide the design of new catalysts with improved performance. Computational chemistry is becoming an increasingly important tool in catalyst development, allowing researchers to accelerate the discovery process and reduce the need for expensive and time-consuming experiments. Imagine the intricate dance of atoms and molecules as they interact on the surface of a catalyst. These interactions are governed by the laws of quantum mechanics, which describe the behavior of electrons and nuclei at the atomic level. Understanding these quantum mechanical effects is essential for designing catalysts with optimal activity and selectivity. Researchers are developing increasingly sophisticated computational methods to model these quantum mechanical effects, allowing them to predict the behavior of catalysts with greater accuracy. As you drift closer to sleep, think about the concept of catalyst poisoning. Catalyst poisoning occurs when a substance binds to the catalyst surface, blocking active sites and reducing its activity. Catalyst poisons can be present in the reactants, the products, or the reaction environment. Preventing catalyst poisoning is crucial for maintaining the activity and lifetime of catalysts. Researchers are developing new strategies for protecting catalysts from poisoning, such as the use of protective coatings and the development of self-healing catalysts. The development of new catalytic technologies is often driven by the need to address specific challenges, such as the need to reduce greenhouse gas emissions or the need to develop new treatments for diseases. These challenges provide a clear focus for research and development efforts, driving innovation and leading to the discovery of new and improved catalytic processes. The collaborative nature of catalysis research, with researchers from different disciplines working together to solve complex problems, is essential for addressing these challenges effectively. The future of catalysis is full of promise. As our understanding of catalysis deepens and our ability to design catalysts with atomic precision improves, we can expect to see the development of new catalytic technologies that will transform industries and improve our lives. From the development of sustainable energy sources to the creation of new medicines, catalysis will play a crucial role in shaping a brighter future for all. As you finally succumb to sleep, remember the silent, unseen catalysts working tirelessly to improve our world. From the medicines that heal us to the materials that build our lives, catalysts are the unsung heroes of modern science. Let their quiet efficiency inspire you as you drift into dreams filled with the boundless potential of chemistry. And remember, even in your sleep, the catalysts continue their work, building a brighter, healthier, and more sustainable future for all. Sweet dreams. Let's delve deeper into the fascinating world of catalyst supports. Often overlooked, the support material plays a crucial role in the overall performance of catalyst. It provides a high surface area for the active catalytic material to be dispersed upon, preventing it from clumping together and losing its activity. Think of it like the scaffolding around a building. It provides the necessary structure and stability for the workers, the active catalyst, to do their job efficiently. Common support materials include silica, alumina, and carbon, each with its own unique properties and advantages. The choice of support material can significantly impact the catalyst's activity, selectivity, and stability. For instance, a support with high porosity can allow for better access of reactants to the active sites, while a support with high thermal stability can prevent the catalyst from sintering or deactivating at high temperatures. Consider the analogy of a sponge. A sponge, with its vast network of interconnected pores, provides a large surface area for water absorption. Similarly, a catalyst support with high porosity provides a large surface area for the dispersion of the active catalytic material. This high surface area maximizes the number of active sites available for the reaction to occur, leading to increased catalytic activity. Furthermore, the support material can also influence the electronic properties of the active catalytic material, affecting its ability to bind and activate reactants. This phenomenon, known as metal support interaction, can be a powerful tool for tuning the performance of catalysts. Now, let's consider the historical context. The use of support materials in catalysis dates back to the early days of industrial catalysis. In the Haber-Bosch process, for example, iron catalysts are typically supported on alumina to prevent sintering and maintain high activity. The development of new and improved support materials has been a continuous area of research, driven by the need to improve the performance and stability of catalysts in a wide range of applications. Scientists are constantly exploring new materials and methods for creating supports with tailored properties, such as controlled pore size, high surface area, and enhanced thermal stability. Think about the connection between catalyst supports and nanotechnology. The advent of nanotechnology has opened up new possibilities for designing catalyst supports with unprecedented control over their structure and properties. Nanomaterials, such as carbon nanotubes and graphene, offer exceptionally high surface areas and unique electronic properties, making them ideal candidates for catalyst supports. By carefully controlling the size, shape, and composition of these nanomaterials, researchers can create supports that are perfectly tailored to the specific requirements of a particular catalytic reaction. Imagine a support material made of tiny, interconnected nanocages, each containing a single active catalytic atom. This level of precision allows for the creation of catalysts with unparalleled activity and selectivity. Let's turn our attention to catalyst selectivity, the ability of a catalyst to direct a reaction towards a specific product. In many chemical reactions, multiple products are possible, but only one is desired. A selective catalyst can enhance the formation of the desired product while minimizing the formation of unwanted byproducts. Selectivity is a crucial factor in determining the economic viability of a catalytic process, as it reduces the need for costly separation and purification steps. Think of a catalyst as a skilled traffic controller, directing the flow of reactants towards the desired destination, the desired product, and preventing them from taking the wrong turn, forming unwanted byproducts. Catalyst selectivity is influenced by a variety of factors, including the catalyst structure, the reaction conditions, and the presence of additives. The shape and size of the active sites on the catalyst surface can play a critical role in determining which reactants can bind and react. This is known as shape selectivity. For example, a catalyst with narrow pores may only allow certain molecules to enter and react, while excluding larger molecules. The reaction conditions, such as temperature and pressure, can also affect selectivity by influencing the relative rates of different reactions. Additives, such as promoters and inhibitors, can be used to fine-tune the catalyst selectivity by modifying its electronic or structural properties. To illustrate the importance of catalyst selectivity, consider the production of propylene oxide, a key intermediate in the production of polyurethane plastics. Propylene oxide can be produced by the oxidation of propylene, but this reaction can also lead to the formation of unwanted byproducts, such as carbon dioxide and acetaldehyde. By using a highly selective catalyst, such as a titanium silicalite 1TS1 catalyst, the formation of these byproducts can be minimized, leading to a higher yield of propylene oxide. This increased selectivity translates into significant cost savings and reduced environmental impact. Consider the development of chiral catalysts, which are catalysts that can selectively produce one enantiomer of a chiral molecule over the other. Chiral molecules are molecules that are non-superimposable on their mirror images, like your left and right hands. Many pharmaceuticals and other biologically active compounds are chiral, and often only one enantiomer is therapeutically active. Chiral catalysts are essential for the production of these enantiomerically pure compounds, as they allow for the synthesis of the desired enantiomer in high yield and purity. The development of chiral catalysts has revolutionized the field of pharmaceutical chemistry, enabling the production of new and improved drugs. The design and synthesis of chiral catalysts is a challenging but rewarding endeavor. Researchers are constantly exploring new strategies for creating catalysts with highly specific chiral environments that can selectively bind and activate one enantiomer over the other. These strategies often involve the use of chiral ligands, which are molecules that bind to the metal center of the catalyst and create a chiral environment around it. By carefully selecting the chiral ligand, researchers can fine-tune the catalyst's selectivity and activity. Imagine a catalyst with a tiny, perfectly shaped pocket that only fits one enantiomer of a molecule. This level of precision allows for the creation of highly selective catalysts for the production of chiral compounds. Let's think about how catalysts are used in environmental remediation. Catalysts play a crucial role in cleaning up pollutants and protecting the environment. Catalytic converters in automobiles, for example, use catalysts to convert harmful pollutants in exhaust gases, such as carbon monoxide, nitrogen oxides, and hydrocarbons, into less harmful substances, such as carbon dioxide, nitrogen, and water. These catalytic converters have significantly reduced air pollution in urban areas, improving public health and protecting the environment. Another important application of catalysts in environmental remediation is the catalytic oxidation of volatile organic compounds, VOCs. VOCs are organic chemicals that evaporate easily at room temperature and can contribute to air pollution and smog formation. Catalytic oxidation is a process that uses catalysts to convert VOCs into carbon dioxide and water. This process is used to clean up air pollution from industrial sources, such as chemical plants and refineries. Catalysts are also used in wastewater treatment to remove pollutants, such as organic dyes and pharmaceuticals. Consider the development of photocatalysts, which are catalysts that use light to drive chemical reactions. Photocatalysts can be used to degrade pollutants in water and air, using sunlight as the energy source. Titanium dioxide, TiO2, is a commonly used photocatalyst for this purpose. When TiO2 is exposed to ultraviolet light, it generates electron-hole pairs that can react with pollutants, breaking them down into harmless substances. Photocatalysis offers a sustainable and environmentally friendly approach to pollution remediation. Imagine a self-cleaning surface that uses sunlight to break down dirt and pollutants. This is the promise of photocatalysis. The application of catalysts extends far beyond the examples we've discussed so far. Catalysts are used in the production of a vast array of chemicals and materials, from plastics and polymers to fertilizers and pharmaceuticals. They are essential for the efficient and sustainable production of many of the products that we rely on every day. The development of new and improved catalysts is crucial for addressing many of the challenges facing society, such as the need for sustainable energy sources, new treatments for diseases, and environmentally friendly manufacturing processes. As you continue to relax and prepare for sleep, consider the vastness of the field of catalysis. It's a field that encompasses chemistry, physics, material science, and engineering. It's a field that is constantly evolving, driven by the creativity and ingenuity of researchers around the world. And it's a field that has the potential to make a significant contribution to a better future for all. As you drift off to sleep, let your mind wander through the intricate pathways of chemical reactions, guided by the silent, unseen catalysts that are working tirelessly to improve our world. Sweet dreams.